In this video, I am going to discuss some simple rules for determination of conjugate classes in a point group. Rule 1. This states that if a symmetry operator R commutes with all other symmetry operators of a group, then R forms a class by itself. For example, suppose X is a general symmetry operator in a group and R is a particular symmetry operator, and XR is equal to Rx for all the operators X in a group G. Then left multiplying by X inverse, we get X. This implies that R, from the left side we get R equal to X inverse R X. So whatever symmetry operator you use in this transformation, similarity transformation, you will always get R from R. You will always get R from R. Whatever be the symmetry operator that you use in a similarity transformation. So R is conjugate to itself. This proves this statement. Which operators are of this type? The identity operator, the sigma H operator, and the inversion operator. These three operators are of this type. Whatever be the point group, if sigma H is present, it will commute with all other symmetry operators of the group. If I is present, I will commute with all other symmetry operators of the group, and thus these operators individually form conjugate classes. Next, come to rule 2. Rule 2 states that in an abelian group, each symmetry operator forms a class by itself. If a group is abelian, then AB is equal to BA for all A and B in the group G. For all AB belonging to G, AB is equal to BA. This is the definition of an abelian group. Then if we left multiply by A inverse, suppose we multiply this from the left by A inverse. A inverse B A. This implies that this is E, therefore on the left hand side we have B is equal to A inverse B A. This is a similarity transformation and we get B from B. Again, left multiplying this equation by B inverse A B equal to B inverse B A. This implies that B inverse A B is equal to A. That is, we get A from A, B from B by similarity transformation. So A is in a separate class, B is in a separate class. Every element of an abelian group is in a separate conjugate class. We know examples of abelian groups, point groups. For example, C to V is an abelian group, C to H, D to H, and all cyclic groups Cn are abelian. There may be other point groups also of abelian type, but these are most common. In all these groups, every element is in a conjugate class by itself. Next, come to rule 3. Rule 3 is stated in this way. Suppose there are two different axes of symmetry, P and Q, in an object. Then the rotations C theta P, that is rotation through an angle theta about the axis P, and C theta Q, that is rotation about Q through the same angle theta. These two operations will be conjugate if by a third symmetry operator of the group we can bring the axis P to Q. We can make P to coincide with Q by some other symmetry operation. Then these two rotations will be conjugate to one another. They will form conjugate classes. For example, consider the D3 point group D3. Point group D3 has a threefold rotation axis and three different twofold axes, C2 1, C2 2, C2 3, and a principal C3 axis perpendicular to the plane of the paper. Then these two rotations, both are 180-degree rotations. These two rotations will be conjugate because this axis of rotation can be brought to this one by a C3 rotation about this principal axis. Similarly, these two rotations, 180 rotations, will again be conjugate to one another. In fact, all these three are in the same conjugate class because of the presence of the C3 axis. C3 axis makes this to coincide with this and this axis to coincide with this. So these three, in the point group D3, we have one conjugate class in which there are three twofold rotations. Next, come to rule 4. Rule 4 states that if there are two different symmetry planes, say sigma 1 and sigma 2, two different symmetry planes in an object, then reflections on these two planes, sigma 1 operation and sigma 2 operation, are conjugate if there is some other symmetry operator in the point group which makes these two planes to coincide on one another. For example, consider the point group of chloroform, C3V point group, chloroform molecule or ammonia molecule. This is the C3 axis, and there are three different sigma V planes, sigma 1, sigma 2, sigma 3. Sigma 1, sigma 2 operations, sigma 1 and sigma 2 are conjugate because by this C3 rotation we can bring this plane to this plane. Similarly, sigma 3 also is conjugate to this one or this one because by C3 rotation we can make these two planes to coincide. So in the C3V point group, these three reflection operators are in the same conjugate class. Similarly, you can consider the benzene molecule. In benzene molecule, there are two types of reflections. For example, this is one reflection plane, sigma V1, this is sigma V2, and this is sigma V3. These three planes are conjugate because by the six-fold rotation, there is a six-fold rotation axis perpendicular to this plane. By that rotation, sigma V1 plane, sigma V1 can be brought to sigma V2, and this can be brought to sigma V3. The three planes can be brought to coincide by C60 rotations, C60 degree rotations, C60 rotations. Therefore, 60 degree rotations. Therefore, these three operations, reflection operations, will be conjugate to one another. But by a 60 degree rotation, you cannot bring it to a plane like this. This is also a reflection plane for benzene molecule. This is a sigma D plane, dihedral, sigma D1. You cannot bring sigma V1 to sigma D1 by any rotation about this axis through C60, because this angle is 30 degree, and 30 degree rotation about this axis is not a symmetry operation. Therefore, this is not possible. However, there are two other sigma D planes. One is this, another is this, and another is this, cutting the midpoints of the edges. Sigma D1, then this is sigma D2, and this is sigma D. This one is sigma D3. That sigma D1 can be brought to sigma D2, and that can be brought to sigma D3 by C60 degree rotation operations about this axis. So these three planes coincide, and therefore reflections on these three planes are conjugate to one another. So there are two conjugate classes of reflection type: sigma V1 operation, sigma V2 operation, and sigma V3 operation. This is one conjugate class, and similarly sigma D1 operation, sigma D2 operation, and sigma D3 operation. These three form another conjugate class in benzene molecule, that is in the point group D6H. Benzene molecule has point group D6H. The reflection operators are of two conjugate classes. Now let us come to rule 5. Let us come to rule 5. If an object has an n-fold rotation axis, Cn axis, then the operations C and K and the inverse operation C and K inverse are conjugate if there exists either a sigma V plane or a C2 axis perpendicular to the Cn axis. Again, let us consider the benzene molecule. Let us consider the benzene molecule. Here, the symmetry operators are identity, then C6 square, that is C3, C6 to the power 3, that is C2, C6 to the power 4, that is C3 square, then C6 to the power 5, then a sigma H plane, sigma H operation. Sigma H is the molecular plane. Then multiply these. Sigma H C6 will give you S6 operation. Sigma H C3 will give you S3 operation. Sigma H C2 will give you inverse operation. Sigma H C2 is I. Then sigma H C3 square will give you S3 to the power 5. Similarly, sigma H C6 to the power 5 will give you S6 to the power 5. And there are sigma V3, sigma V operations of the same conjugate class and 3 sigma D operations of the same conjugate class. These two have already been found. Now, we see that C6 and C6 to the power 5. C6 to the power 5 is actually C6 inverse. These two operations are conjugate because of the presence of a reflection plane like this. There are many reflection planes. If even a single reflection plane containing the principal axis is present, or containing the rotation axis is present, then the rotations and its inverse operation will be conjugate. Similarly, we have C3 operation and C3 square operation. These two are inverses of one another and they will form a conjugate class for the same reason, because of the presence of a sigma V plane like this. And this rule is also valid for improper rotations. This same rule is also valid for improper rotations. And therefore we can say that S6 and S6 to the power 5, which are inverses of one another, will form a conjugate class. Similarly, S3 and S3 to the power 5, S3 and S3 to the power 5, S3 and S3 to the power 5, they will form a conjugate class. Thus, using these simple rules, we can find all the conjugate classes in a point group. The long similarity transformations will not be necessary, and the number of conjugate classes is a very important parameter in the representation theory of groups. With this, I complete my discussion today. Thank you very much for watching the video.